Okay, a very good morning to all of you. And we are meeting after a couple of weeks, and this is because of this coronavirus and all. We have to take the classes online. For the time being, the offline classes are off. I hope you have given the midterm very well. I have got some. I know there were some issues regarding the midterm, and I think I will be able to get rid of them once the college reopens. So for the time being, we'll be conducting all the classes online. So I'm starting it today, and all the teachers of mathematics department will also take your classes online. Now, before I start my mode of teaching today, I just tell you that in what mode actually I'm going to teach you. Basically, what we'll do is that we'll be actually we have created a Google Classroom. I think you have got the class codes, and perhaps by this time, all of you have joined the classes with the respective codes. So we have made 12 classes. So there are two corresponding 12 class codes in the Google Classroom. And what you need to do is that you have to just join those classes, and you will see that there will be announcements made for time to time, and there will be announcements, as well as we'll be providing you the link where you can see the videos and the live streams and all. And also you'll be getting the study materials what we are teaching over here, as well as the assignments, and then of course we'll have the online test. So what we'll do is that initially, as far as my class is concerned, I have decided that I'll be uploading a recorded video, and I'll give you the link. So once the class starts, you have to go to that video. The video will be of 20 to 30 minutes. Okay, it depends on the topic. And after going to the video, okay, there will be a 5 to 10 minutes of online discussion, and at that time I'll be live. So you have to go carefully through all the points of the video, and if you have any doubt, then you can clear your doubt during those 5 to 10 minutes which I'll be live with you, right? And apart from that, I'll be also live while the video will be played. You can write your comments on the chat box, and I'll be if possible, I'll be able to answer those questions. If you like, that's the other way you can communicate with me. But though after half an hour, there will be 5 to 10 minutes of discussion regarding the topic that I'll be teaching you today, okay, which you will see in a recorded form. Now, after the question answer session, there will be basically 20 minutes of problem solving. That is the topics that I have taught today. I'll be giving you some assignments which you need to do, and those assignments will be given through the Google Classroom only. What you have to do is that you have to just download those assignments. It will be in the form of a PDF, and you have to solve those assignments within the class only, and then you have to upload those assignments, okay, in the Google Classroom, right? So it should be handwritten, because I'll be giving you subjective questions. I won't be giving you MCQ questions for the assignment, because we'll be having an online test followed by that. So basically this will be subjective questions. So you must be ready with some white pages, or your notebook or something like that, where you can do those problems, and then you can scan those pages or take a peek of those pages, and in whatever manner, either in the JPEG format or in the PDF format, you can upload those in the respective Google Classroom. So once the assignment part is over, then we will move on. We might give you 5 minutes of interchange, and then we will go to the online test, which is the final part of the class. And the online test, all of you know, you have been giving the online test when you were doing the classes in offline form. And it will be through the IEM-CRP as usual. There will be 5 to 10 questions, and we have to answer in 10 to 15 minutes. So that's all overall structure of basically how will I go in a particular class, because each class now is of 1.5 hours. So I have to utilize those time, because what will happen is that I don't know when the college will get reopened, probably in the middle of April. Then after that we don't have much time. Second midterm will come, so we need to make use of this online facilities available to us. I hope you will cooperate with me, and so that I can complete the syllabus within time. So without discussing further, I will one more thing. In the Google Classroom, you'll see that there's an announcement already made. Whatever I have told, it's already given in step-by-step form. So just go through it. So first step is you'll be getting a YouTube link. You have to just go to the YouTube link and study it for 20-25 minutes. Okay. Then after that, there will be 5 to 10 minutes of online discussion where I'll be live with you, for which you will also get another link. Okay. That will be through YouTube Live, through our IEM-Math&Stat channel. And once that is over, I'll be giving you assignments to solve through the Google Classroom, which you have to solve it. And once that is over, finally you'll be giving an online test, as you normally give in a normal class, right? So that's all, this overall situation. And I'll be also uploading the study materials, which I'll be discussing in the video, so you don't have to write the notes, okay, as the video progresses. You don't have to do that. Okay, you just pay attention to what I'm teaching actually in the online mode. So that will be much more beneficial, because whatever I am actually displaying on the board, basically that will be given to you through the Google Classroom. So you don't have to worry about that. So don't make a note. So no point of doing it. Try to understand it. Okay. And basically you have to create a email ID. I think you have done by this time. And you have to just log in with that ID in the Google Classroom, and that's all you have to do. And you must have a good internet connection, okay, and because you have to access the YouTube also. So there will be a link, and that will redirect to the YouTube, right? So that's all you actually need to get this online classes going smoothly as far as maths is concerned. What I'm going to do is that I'm basically going to teach from a PDF and send it in PDF. Basically, I've written something in my hand, and I've just scanned it and made it a PDF, and from where I'll just try to explain the properties and topics of the Laplace transform, which I was teaching actually. So that's what I'll do actually, because I'm using a software called OBS, by which we are capturing the screen in my laptop, and that is actually being displayed, which you are seeing in the form of a video. So without talking much more, I will just go directly into today's topic. So if you remember that before the first midterm, we were actually discussing convolution theorem. So that part I have covered. Convolution theorem is a very, very important property of Laplace transform, by which we can find out the inverse Laplace transform. So that part we have already covered. And now we come to another very important aspect in Laplace transform, is finding the Laplace transform of periodic functions. Now before I go into how to find out the LT of a periodic function, you must know what is a periodic function, because unless you are not clear about that, there's no point of progressing further. So what is a periodic function? I think most of you know what is a periodic function, because you have done physics, maths in +2 level, and this is a very elementary thing. I'll be going, I'll be defining you what is actually a periodic function. As the name says, periodic. It says periodic means it refers to a period, basically, and period means basically a unit of time, a time interval. So a periodic function is something which actually repeats after a certain unit of time. Let's say I say that ft is a periodic function with period a, small a. Then it means that when the function is at ft plus a, at t plus a, then ft plus a will be actually equal to ft. Then again you increase a unit of time, it becomes ft plus twice a. So at ft plus twice a, the function will be equal to ft. And this goes on. At t plus 3a, again the function repeats. At t plus 4a, again it repeats. So it goes on repeating after every a units of time. If that happens, such a function is called a periodic function. and the constant unit of time after which the function gets repeated on and on and on is called the period of the function. So if you look at the PDF that I have made, I said that let ft be a periodic function of period a, so that, which I was saying, your ft will actually be equal to ft plus a, because after a units of time the function is repeating. Then again you add a units of time, that is at t plus twice a, it is f of t plus twice a, which is equal to ft, and that's also equal to ft plus thrice a. So it goes on repeating after every a units of time. So that's the main thing, and then property of a periodic function. Very good examples are the trigonometric functions. The sine function, the cosine function are good examples of periodic function, because they are periodic function of period 2 pi. Because you see 2 pi, after 2 pi units of time, the sine and cosine function gets repeated. Like in case of tan function, it is also a periodic function, but the period is different, the period being pi. So there are a lot of periodic functions where the function gets repeated after a certain unit of time. Right, now my question is to how to find the Laplace transform of those periodic functions, because Laplace transform is basically a transform of a function from time to the frequency domain. So it may happen that the function of time which you are trying to take the transform is a periodic function, right? So if I want to find out a Laplace transform of periodic function ft whose period is a, let's say we assume initially that ft is a periodic function whose period is a, I'm talking of small a, then if I want to find the Laplace transform of that periodic function, I will use the basic definition of Laplace transform. So if I use the basic definition of Laplace transform, then I'll get L of ft equal to integral 0 to infinity e to the power minus st into ft dt. Now this integral, from the very basic property of definite integral, can be represented in the form of, or can be, as I say, can be written in the form of integral 0 to a e to the power minus st ft dt plus integral a to twice a e to the power minus st into ft dt, and like that plus e to the power twice a to thrice a e to the power minus st into ft dt, and like that it will continue right up to infinity. Because what we are doing is that we are breaking the interval 0 to infinity into equal subintervals 0 to a to twice a to thrice a to 4a, and like that. So there will be infinite intervals because the upper limit is infinite, it's improper integral. Now what I am going to try to do in this way to find out the Laplace transform of periodic function of period a, I will try to represent all the integrals from second integral and onwards in the form of the first integral. You see, I have written in the sum of an infinite integrals. What I am trying to say is that I will be trying to represent the second, third, fourth, fifth and all the remaining integrals in terms of the first integral, and that can be done. Now how that can be done? Now if you consider the second integral, just look at the second integral very carefully. It is integral a to twice a e to the power minus st ft dt. Now how do I convert this integral in terms of the first integral? That is the question. So what we do is that we put small t equal to capital T plus a. We just make a substitution. In place of small t, I just put capital T plus a being the period of the function. Now that we can always do. If we do that, taking differential on both sides, I get dt is equal to d capital T. I find out the limits of capital T when small t is equal to a, capital T is equal to 0. When small t is equal to twice a, capital T is equal to a. So making those changes, the integral a to twice a e to the power minus st into ft dt. Now this becomes equal to integral 0 to a, because corresponding limits gets changed. In place of small t, I write e to the power minus s into capital T plus a, and in place of small t, I write f of capital T plus a. dt being replaced by d capital T. Right? It's very simple. Now, you know s is a constant, a is a constant. So, e to the power minus s is a constant. So, I can take e to the power minus s outside the integral. If I do that, I'll be getting something like this. E to the power minus s integral 0 to a e to the power minus st into f t plus a dt. Right? Now, what I can do in this integral is that in place of writing capital T, I can replace capital T by small t. I can do that always. Because you very well know the variable of an integral is immaterial in a definite integral, which I have written it down. So in place of t, if you write capital T or capital U or V, doesn't matter. What it matters is the integrand. So if I substitute in place of capital T, write small t, it doesn't matter, e to the power minus st f t plus a dt. Okay. Now we told initially that ft is a periodic function. So if ft is a periodic function, ft plus a will always be equal to ft. So in place of ft plus a, I put the value ft. And on the moment I put the value of ft in place of ft plus a, I find that I have represented the second integral, that is a2 twice a e to the power minus st into ft dt, in the form of the first integral e to the power minus s integral 0 to a e to the power minus st ft dt. Okay, so this is the first thing that we do. In a very similar manner, I can represent the third integral in terms of the first integral. Just like we did in the case of the second integral, we can do it also for the case of the third integral. Now, how we can do it? So, again by the same procedure, I mean by the process of substitution we can do it, but the substitution process will be a slightly different than the one that we did in the previous case. This time, the integral, the third integral is twice a to thrice a e to the power minus st ft dt. Now, if I want to convert this integral from 0 to a, I have to make a substitution. In place of small t, I'll put capital T plus twice a. Because if I put capital T plus twice a, I can change the limits from 0 to a. And that's all. That's the simple logic is why we are putting capital T plus twice a. And on putting that, I see that d small t is equal to d capital T. And as I was telling you that if you take the limits will become 0 to a, which is coming. And so I put all those substitutions in the third integral. And this is what the third integral now looks like. So if you make those substitutions in place of small t, capital T plus twice a, so you get integral 0 to a e to the power minus s capital T plus twice a into f capital T plus twice a dt, d capital T. Now again, as you can see, s is a constant, twice a is a constant. So e to the power minus twice s being a constant is taken outside the integral. So you are left with integral 0 to a e to the power minus st into f capital T plus twice a dt. Then, like in the previous case, we write in place of capital T small t, which we can always do because the variable of integral is immaterial in a definite integral. So it doesn't matter. What matters is the integrand. So if I write small t in place of capital T, it does not affect the integral. So therefore I can do it. If I do it, one thing is clear, that since ft is a periodic function, I can replace ft plus twice a by ft. And on doing that, I get something like this. That means I get in the third integral from twice a to thrice a e to the power minus st ft dt to be equal to e to the power minus twice as integral 0 to a e to the power minus st into ft dt. Because I told you earlier that ft plus twice a is equal to ft. So my objective has been fulfilled. That is, my objective was to represent the third or the second integral and onwards in terms of the first. We have done for the second integral. We have now just now have done for the third integral. So like this, if we proceed, we can actually represent each and every definite integral from second integral and onwards in terms of the first integral. We can do that. I've shown you two cases. Third, fourth cases can easily be done, but you need not to show it. So if you do that and make those substitution back in equation number 1. Equation number 1 was this equation, which I wrote from the definition of Laplace. This one, you see, this is equation number 1 is written over there. This is equation number 1, right? The first equation from the definition of Laplace transform that we did. This was equation number 1. So in this equation number 1, I substitute in place of the second integral the result that I have got, in place of third integral the result that I have got. All are in terms of the first integral. So what do we get? We get something like this. We get something like this. This is the one that we get. So we get 0 to a e to the power minus st ft. That was the first integral. That remains unchanged. Then we get the second integral in terms of the first. So we get plus e to the power minus s integral 0 to a e to the power minus st ft dt. Third integral in terms of the first, just now we did e to the power minus twice s integral 0 to a e to the power minus st ft dt. And in this way, we can write the remaining integrals 4, 5, 6, 7, 8 and right up to infinity. So dot 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 up to infinity. Now from this is very much clear that I can take the integral common from all the terms. So I am doing that. If I do that, I am left with the term in the first bracket, which you are seeing now in front of your screen. This is what you are seeing. So what we get? 1 plus e to the power minus s plus e to the power minus twice s plus dot 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 up to infinity multiplied by the common term, which is the integral actually, integral 0 to a e to the power minus st ft dt. Now if you look at the expression of the first bracket, you can recollect that what it is. It is basically a infinite geometric series. So when we say infinite geometric series, we all know what is the sum to infinity. It is the first term divided by 1 minus common ratio. So what is the common ratio then? The common ratio for this series is e to the power minus s. And the first term is 1. Okay, so it's a by 1 minus r. If you apply, you get it to be equal to 1 by 1 minus e to the power minus s. That's what we are getting. You see, I've written it over there. Multiplied by the integral that was already obtained earlier, 0 to a e to the power minus st into ft dt. Okay. So this is the result that we get for finding out the Laplace transform of a periodic function. So if I say that if ft is a periodic function with period a, okay, then the Laplace transform of that periodic function will be 1 by 1 minus e to the power minus s into integral 0 to a e to the power minus st ft dt. So that is the end result of finding out the Laplace transform of a periodic function. I hope it is clear. So if it is clear to all of you, it's not a difficult topic at all I'm teaching. So we can discuss, I'll be rather discussing, not you're not able to participate. So I'll be doing a couple of problems related to the Laplace transform of a periodic function. Okay. So I have chosen this problem. You can see, find the Laplace transform of this function ft, and ft is equal to t from 0 to pi, pi minus t from pi to 2 pi. It's given that ft is equal to ft plus twice pi. Right, so that's given. Now you have to find the Laplace transform of this function. Now the first thing that should strike in this problem in your mind, we are just for now we were doing that. is the function is periodic. You see clearly it's given in the last line, ft is equal to ft plus twice pi, which means that the function repeats after 2 pi units of time. So it's a periodic function definitely, with the period being 2 pi. Now, if it is a periodic function of period 2 pi, then we will actually apply the result that we have just now derived. So the period being 2 pi, so if we take the Laplace transform of the function of ft, so I get, as per the result, is 1 minus e to the power minus twice pi s, integral 0 to 2 pi e to the power minus st ft dt, because 2 pi was the period, so it is 0 to 2 pi. Now then we have to perform the integration. So now then, actually looking at the function, this becomes 1 by 1 minus e to the power minus twice pi s. Then what we are doing is that, as per the definition of the function, from 0 to pi, ft is t. So I write e to the power minus st into t dt. And then from pi to 2 pi, the function given there is pi minus t. So I write e to the power minus st into pi minus t dt. From pi minus t in dt, yes. And the limits are from pi to 2 pi. And then I just perform integration, very simple integration by parts you have to apply. So if you apply integration by parts, you will be getting something like this. So outside we had 1 minus e to the power minus twice pi s. And then if we do integration by parts, so we get the rest term. So it's t, the second function is the exponential function in this case here. So t into e to the power minus st by minus s minus ddt of t, which is 1, into integral of e to the power minus st by s, which is e to the minus t by s square. Okay. And then if you do the same thing here in this case, plus pi minus t, integrate by parts, and you should get this result. And then you have to put the respective limits using the fundamental theorem, and you will arrive at a solution, right? So you get 1 minus minus e to the power minus twice pi s, and if you put the upper limit here, which we are doing in the first term, you see, look at the first term here. Here actually we are putting pi at, you see, lower limit is 0 already. So you put pi, so you get minus pi by s into e to the power minus s by pi. Okay, and then you see at the lower limit it is 0, because you see at it is t equal to 0 to pi, so lower limit is 0. Then the next term is minus 1, so therefore if I put t equal to pi, so it's e to the power minus s pi by s square, and at t equal to 0 it is e to the power minus st is actually 1, so it's not 0. So it's 1 by s square plus 1 by s square, right? Similarly, you just use the fundamental theorem and find out the results of this. You put the upper limit and lower limit, and you get an expression something like this, right? So once this is obtained, okay, now we make a bit of simplification. From what we do is that we take minus pi by s into e to the power minus pi s common from the first as well as the fourth term. So if we take it common, what do we get? 1 minus e to the power minus pi s. Okay. So then we take minus 1 by s square into e to the power minus pi s common, and we get 1 minus e to the power minus pi s. And finally, if we take 1 by s square common from the two terms, leftover terms, you get 1 minus e to the power minus pi s. So overall, 1 minus e to the power minus pi s is common, and you are left with something like this. So it is 1 by 1 plus e to the power minus pi s into pi minus s, minus pi by s into e to the power minus pi s minus 1 by s square e to the power minus pi s plus 1 by s square. Okay, so that is written in this form, because if you simplify a bit, taking the same s square, you will get 1 minus 1 plus pi s into e to the power minus pi s divided by s square into 1 plus e to the power minus pi s. So which is the required Laplace transform that is being asked in the question. So it's a very straightforward. The only thing is that you have to perform the integration correctly and don't make any mistake, because finding the Laplace periodic function will be very easy because period will be mentioned, and hence you just find it out, provided you don't make any mistake in the integration. Okay. Next is the second problem which I am going to discuss here is that find the Laplace transform of ft where ft is equal to a sine pt, where 0 less than t less than pi by p, and 0 when pi by p less than t less than 2 pi by p. Okay. It's given that ft is equal to f t plus 2 pi by p. Okay, 2 pi by p. So from the last statement in the problem, it is very much clear that the function is a periodic function, the period being 2 pi by p. So if it is a periodic function, once you've identified it, it becomes easier for you to proceed. The period being 2 pi by p, that's very important. So therefore, if you use the formula of the Laplace transform of periodic function, because we have already observed that it's a periodic function, so we'll get 1 by 1 minus e to the power minus twice pi by p into s, because twice pi by p is a periodic function, so it's minus twice pi s by p. So into integration of 0 to the period, which is 2 pi by p, e to the power minus st into ft dt. So now then we break this integral 0 to 2 pi by p into 0 to pi by p integral e to the power minus st into a sine pt dt. Okay, and you can take this a outside if you like, should do that, and then if you integrate, is this integration is e to the power ax into sine bx dx form. Now this integration can be easily performed by integration by parts, but I suggest that you should be knowing the result, which we call it a standard result of standard integrals. There was a topic called standard integrals which you did in plus 2 level, and from that I can take the help of the result e to the power x, integral e to the power x into cos bx dx. So that integral will actually be equal to e to the power x by a square plus b square into b sine bx minus a cos bx. So that is the result that we are going to apply here, since it's a standard integral. So if you know the result, then it will be benefit for you, because you don't have to work out again. Otherwise you work out again, and for that you don't get any extra credit, because at this level you must be knowing the result of standard integrals, which is required at higher engineering mathematics. So we put that result directly over here using the result which I told you, e to the power minus st by s square plus p square into minus s sine pt and minus p cos pt. Okay, and then we put the limits 0 to pi by p. So if you put the limits from 0 to pi by p, you get something like this. You get a by s square plus p square can be taken outside into 1 minus e to the power minus twice pi s by p, and into p e to the power minus pi s by p plus p, right? And then on a bit of simplification, if we take that p outside, which you should always do, so you are left with ap into 1 plus e to the power minus pi s by p, right? Because if we take p common, you should get that factor left behind. And then so you get ap into 1 plus e to the power minus pi s by p whole divided by a square plus p square into 1 minus e to the power minus twice pi s by p. Now it is very much clear that I can basically write 1 minus e to the power minus twice pi s by p as is in the form of a minus b into a plus b, because it's a square minus b square form. So if you write in a square minus b square, what is the advantage of writing that? Because I can cancel the factor in the numerator, because I can write 1 minus e to the power minus twice pi s by p as 1 minus e to the power minus pi s by p into 1 plus e to the power plus pi s by p. Okay, sorry, 1 plus e to the power minus pi s by p. Now we can do that. Now on doing that, the factor 1 plus, the plus factor will actually get cancelled, and you will be ending up with a result like this, equal to AP by S square plus B square into 1 minus e to the power minus pi s by p. So this is the way we find out the Laplace transform of a periodic function. Okay, so that's all for today's class. We'll be discussing more on Laplace transform in the next class, and for the time being we call the class off, and I'll be coming online very soon. And if you have any queries regarding this topic of Laplace transform periodic function, you can put up your questions over there, and I'll be able to answer you. And then we'll be having an assignment, and then finally with the online test. Okay, thank you so much.